All right, so part of what we're going to do now is we've set up our kinematics equations. Now we need to see how we're going to work with those in problems. And so basically, in our kinematics problems, we're going to deal with two types of motion. So either we're going to have motion with a constant velocity, in which case the acceleration is zero, the initial velocity. The velocity will always be equal to the initial velocity value, whatever that is. And we really simply have a single equation that describes how the position is changing as our object moves around over some chunk of time. A motion with constant acceleration is a little bit more complicated, but what we're doing is we're saying that the acceleration is simply equal to some value, right, whatever it was at some initial point. And then here we have a velocity equation that'll tell us how the velocity is changing with respect to time. A position equation that will tell us how the object's position is changing with respect to time, and notice that it's quadratic. And then we've got an equation that we can use to relate all these quantities that doesn't include time. So we've got sort of our four equations here that we'll end up using within a problem. So one if we've got constant velocity motion, these three if we've got constant acceleration motion, two that include time, one that doesn't. Now some of the other complications that we'll see within problems is, well, maybe we'll have multiple objects within a problem. So to make a kinematics problem more complicated, instead of having a single object, maybe we'll have multiple objects. Or instead of having a single object moving along a single dimension, maybe we'll have a single object that's moving in multiple dimensions. So something where we're told about its motion in both the x and y. So basically what we want to do then is we want to get comfortable making sure that we use the right equation. So what we want is to figure out, how do I make sure that I've got the right equation in my kinematics problem. Now part of this is I need to know what the limitations are for each of these equations and when I can use them and when I can't. And so there's a series of questions that we'll basically walk ourselves through. So notice that for each object or dimension, we need to ask the following question. So if you've got a single object moving in a single dimension, so say an object moving in the x or an object moving in the y, then you really need to only ask this once. But if you've got multiple objects, so say I've got both a car and a bike moving in the x direction, then I'll need to ask these questions for both the car and the bike. Or if I've got let's say a projectile problem that's moving in both the x and y, then I'll need to ask these questions for both the x and y components. So what are my set of questions then? Well, the first one's just going to be, what do I know? And so what this question is doing is it's basically saying, all right, can we figure out, in terms of these five vector quantities, acceleration, initial velocity, initial position, final position, so our five vector quantities and then the scalar quantity time, what information do I already have? What have I been given within my problem? And then we're going to ask, once we figure out what we know, the next question we're going to ask is the acceleration of the object zero? So if it is, what that tells us is that we clearly have a constant velocity motion problem. And since it's constant velocity motion, there's really only one equation to describe it. So basically, if we know we have constant velocity motion, then we know which equation we want. If the answer to this question is no, then we're going to go to an additional question. And so we next need to ask, is the acceleration constant? And this may seem like a really sort of simple question, but it's actually kind of crucially important, because if the answer to this question is yes, the acceleration is constant, then we can use our constant acceleration equations. But if the answer to this question is no, we can't use the constant acceleration equations that we have. So we'll see plenty of problems where an object will move and the acceleration of the object will not be constant during that motion. If that's the case, we don't want to use our constant acceleration kinematics equations. So this is I need to make sure that the equation I'm using is valid for the problem I'm trying to work. And so that's really the guts of this question. If I'm going to use constant acceleration kinematics equations, I really do need to make sure that I have constant accelerated motion. So let's assume that the answer is yes. We know that we have constant acceleration motion. So again, we've got another question. So do I know or want to know time? And if the answer to this question is no, well, we only have one of our three constant acceleration equations that doesn't include time. So if I don't need to know time, if I don't know it or don't think I need to know it, I can get away without having that information, then this is probably the equation that I want. 9 times out of 10, using this equation will take me straight to the answer. If I do know time, then I probably need an equation that includes time in it. And so in that case, I need to ask one more question. And basically in this case, it's, well, what do I have more information about? Do I have more information about what the positions of the object are, or what the velocities are? So if I know more about the position, so let's say I know the initial position and final position of the object, then the position as a function of time, this equation, is probably going to be one that I can use to solve for what I need to solve for. If, on the other hand, what I know are the initial and final velocities, so notice this equation has both the initial and final velocity and time in it, then my velocity as a function of time is probably going to be the more useful equation. So all this is doing is it's basically using these 5 questions to make sure that we're using an equation that we can, and then to help us figure out what is probably the most useful equation in terms of going ahead and solving the problem. So let's see how this works out in an example. So here's a simple example. I'm told I've got a motorcyclist that travels along a long straight stretch of highway. Initially he's traveling at a speed of 25 meters per second. The road sign informs him that he is approaching a small town and needs to slow to a speed of 10 meters per second. If the small town is only 300 meters past the road sign and he slows at a constant rate, what is the cyclist's acceleration? And how long will it take him to slow down? Okay, fine. I notice I've got 2 questions here, so I want to solve for the cyclist's acceleration in one, and then I want to solve for time in the other. Right? How long will it take him to slow down? And so like with any good problem, I'm going to start by turning the word problem into the right picture. And again, with a kinematics problem, because I'm interested in both what's going on initially and what's going on at the end, I'm actually going to make 2 pictures. So here's the motorcycle initially. Here's its initial velocity vector. I know it's got a magnitude of 25 meters per second. And then here's the motorcycle at the end. So here's the final position. Here's its final velocity. So I know this vector, the final velocity vector, has a magnitude of 10 meters per second. I know the acceleration has to point back in the opposite direction because my motorcycle is slowing down. And if I pick a coordinate system so that the origin is where the motorcycle started, right, where it was initially, so the initial position vector would be 0, then the final position vector is just going to be this 300 meters further down the road in what I've called the positive x direction. So here's notice what I've done is I've drawn my picture, really drawn 2 pictures, right? Initial motorcycle, final motorcycle, and then drawn the 5 vectors that I care about on top of that picture. So now I'm going to come through and see what I know. So again, the first question is, well, what do I know? Well, thinking about each of these 5 vector quantities, starting with the acceleration. Well, I don't know its value, but I do know its sign. So what I'm going to do is I'm going to say, well, the acceleration is some value, I'm going to call it A. And I'm just going to denote here that I know that the sign of that acceleration value has to be negative because it points back to the left, which is what I've called the negative direction, the negative x direction. The initial velocity points in the positive direction. It has a magnitude of 25 meters per second. The final velocity also points in the positive direction. It has a magnitude of 10 meters per second. The initial position, well, the motorcycle started at the origin, so its initial position is 0. And it went 300 meters further down the road in the positive x direction, so its final position is positive 300 meters. Time, I don't know. So here are my 2 unknowns, the acceleration and time. And to show that that makes sense, well, if I come back to my sort of initial problem, I was given 2 questions. The first one is, what's the cyclist's acceleration? There's one unknown. The second, How long will it take? What's the time? So sure enough, the two questions I'm being asked correspond to the two unknowns that I've got sitting here in my problem. All right, so for the first question, what's the cyclist's acceleration? And here's the information I have. So this is what I know. So my next question after this is, well, is the acceleration 0? And here I know that it's not 0 because the velocity is clearly changing, right? My motorcycle is slowing down, so it has to have a non-zero acceleration. Is the acceleration constant? That was the next question. And in this case, we were told in the problem to assume that the motorcycle slows at a constant rate. That's a fancy way of saying, sure enough, our acceleration here is going to be constant, so I know I can use one of my constant acceleration equations. The next question, do I know time? And the answer is no, I don't. So what I'm going to do is I'm going to say, well, if I don't know time, let me see if I can use the equation that doesn't include time. So here's my constant constant acceleration equation that does not include time. And as I look at this, final velocity, 10 meters per second. Initial velocity, 25 meters per second. Acceleration, that's what I want to solve for. Final position, 300 meters. Initial position, 0 meters. So sure enough, there are 5 variables in this equation, but I have a value for 4 of them. So I can solve this immediately for A, and so algebraically it just says, well, what I need to do is I'll bring the initial velocity over onto the other side of the equation, then I'll divide by 2 and divide by my displacement, so I'm left with this as an expression for the acceleration. Now I can plug in my values and check my units. So plugging in my values, I end up with an answer here. I calculated out an answer of negative 0.875 meters per second squared. If I want to check and make sure that my units are correct, one of the things I can do is, again, I can do the dimensional analysis of this expression. So if I take velocity squared as a unit, so meter squared over second squared, divide by 2 is unitless, the displacement's going to have units of meters. Sure enough, I end up with meters per second squared. So I can always come back and do the dimensional analysis to make sure that my units work out. So a couple of things to check first. First, did we include units? We'd hate to throw away points by not including them. Sure enough, we've got them. They're right there, meters per second squared. We've even said there's a way to check and make sure that those units are the right units. Second thing to check, does the sign make sense? Well, I got a negative answer. But if you remember, when we were setting up the problem, we said I know that if my velocities point in the positive direction, the acceleration has to point in the opposite direction because the motorcycle is slowing down. So sure enough, I needed a negative answer. So yeah, my sign here makes sense. So now, the second part of my question, how long will it take him to slow down? So now notice, basically I'm saying, well, I know all of these values. The only thing left is t. I've got 2 more equations. I could use either of them to solve for time, but in this case I'll use the easier one because it's just easier to use, so I'll use my velocity equation to solve for time. I'll do it algebraically first, so again take the initial velocity value over, then divide by the acceleration. Then I'll come back and plug in my numbers. And notice I'm going to have 10 minus 25, that's minus 15 on top, but then I'm dividing by a negative value, so I get a time that actually happens to be positive, so 17.9 seconds. So again, did I include units? Yep, it's going to be seconds. Again, I can do the dimensional analysis to check. And then does my sign make sense? Well, I know that I should have a positive value of time because it happened after he initially started slowing down, and that was at t equals 0. So sure enough, my sign makes sense for what my time is. Now the other thing that's interesting is we've used 2 of our constant acceleration equations to solve for the problem. We can actually use the third to check and make sure that we've got the right answer. So if I come back and use my position equation, so position is a function of time, the one that we didn't use in solving, and now I can plug in everything on the right-hand side. Now that I've got my values for time and acceleration, I can plug everything in on the right-hand side, and check and see if I do in fact get the final position. So when I plug in initial position 0, initial velocity 25 meters per second, time is 17.1, plus 1/2 times the acceleration of negative 0.875 times time 17.1 squared, calculate that out, I get a final position of 300 meters. Sure enough, that's exactly where the motorcycle ends up in the problem. So I can actually use all three of my equations here, 2 to solve, the third to check and make sure that I've got the correct solution. So this is how we're going to solve these kinematic problems. And the only thing that we're going to really do to sort of make things more complicated is, again, just add more objects, got 2 objects going, and then more dimensions. I'll have an object that's moving in both x and y, so I'll need to keep track of 2 dimensions, or 2 objects, to simply make the